In mathematical logic, as you know, the or sentential connective by default is taken in an inclusive sense. However, there is in fact an exclusive or in mathematical logic, and in this video I'm going to cover that very briefly. Now first off, if we have a statement such as this, P or Q, we're using the or in an inclusive sense. That is, P or Q is true if at least one option is true, but both can be true. Whereas in an exclusive or, so we have P exclusive or Q, that's true if only one option is true, but both cannot be true. And we can illustrate this most easily with a truth table. We have the atomic sentence P, we have the atomic sentence Q, and then the molecular sentence P or Q. P can take the truth value being true, Q can be true, P can be true, Q can be false, P can be false, Q can be true, and P can be false, Q can be false. True or true is true, true or false is true, false or true is true, and false or false is false. The inclusive or is only false when both P and Q are false. But this first row really is most important when we're considering this inclusive or sense, because both P and Q can be true for the statement as a whole to be true. In contrast with the exclusive or, which is not only symbolized with this symbol here, but sometimes it's just called XOR, it's not going to be true if both P and Q are true. So let's construct the truth table. We have the atomic sentence P, the atomic sentence Q, and then molecular sentence P exclusive or Q. P can be true, Q can be true, P can be true, Q can be false, P can be false, Q can be true, and P can be false, Q can be false. If both are true, we get something that's false. True or false is true, false or true is true, and false or false is false. So here, with the first row, we see the difference. Here we have our exclusive or, whereas in inclusive or, P and Q can both be true. Moreover, note that if we have the statement, parentheses, P or Q, close parentheses, and not, parentheses, P and Q, close parentheses, that's logically equivalent to P exclusive or Q. On the left-hand side, we have this P or Q, so P can be true, Q can be true, or both P and Q can be true. But then we're saying, and it is not the case that both P and Q are true. So this left-hand side and this right-hand side are logically equivalent. And we can also show this with the truth table. We have the atomic sentence P, the atomic sentence Q. We have the disjunction P or Q. We have the conjunction P and Q. We have the larger molecular sentence, not, parentheses, P and Q, close parentheses, and the even larger molecular sentence, parentheses, P or Q, close parentheses, and not, parentheses, P and Q, close parentheses. And then finally we have P exclusive or Q. So P can be true, Q can be true, P can be true, Q can be false, P can be false, Q can be true, and P can be false, Q can be false. We have this disjunction in the inclusive sense. So true or true is true, true or false is true, false or true is true, and false or false is false. Then we have a conjunction, P and Q. So true and true is true, true and false is false, false and true is false, false and false is false. We have the negation of the previous column of that conjunction. So true to false, false to true, false to true, false to true. We have the conjunction of this column here, this disjunction, and this column here, the denial of a conjunction. So true and false is false, true and true is true, true and true is true, false and true is false. And then finally we have our exclusive or, looking at this column and this column. So true, exclusive or true is false, and then true or false is true, false or true is true, and false or false is false. Compare the last two columns. They represent the two molecular statements at hand. They have the same exact outcomes, and so this statement here and this statement here must be logically equivalent. And so we have taken a look at the inclusive and exclusive OR in mathematical logic.